Dear friends, in this class let us discuss about an important theorem which is known as Gauss lemma. So the lemma states that for n congruence to 0 mod p, and consider the least positive residue mod p of the following p minus 1 by 2 multiples of n. P minus 1 by 2 multiples of n means that is n, 2n, 3n, etc. up to p minus 1 by 2 of n. If m be the number of residues which exceeds this p by 2, then n by p equals minus 1 power m. So this is Gauss lemma. When n is incongruent to 0 mod p, then the p minus 1 by 2 multiples of n, that is n, 2n, 3n, etc. to p minus 1 by 2 n, with the least positive residue mod p of this p minus 1 by 2 multiples of n. If m be the number of residues which exceeds this p by 2, then n by p equals minus 1 power m. It's an important result that is known as Gauss lemma. How to prove this one? So, consider the statement. n incongruence to 0 mod p. n is incongruence to 0 mod p. Also we know that 1, 2, etc. to p minus 1 by 2, all of these are incongruence to 0 mod p, since p be an order, right? Then clearly, since n is incongruence to 0 mod p, then all of these n, 2n, 3n, etc. p minus 1 by 2 n are incongruence to 0 mod p. Agree? n, 2n, 3n, etc. p minus 1 by 2 n are incongruence to 0 mod p. Now we consider their least positive residues and distribute them into disjoint sets A and B according as their residues less than p by 2 and greater than p by 2. We consider the least positive residues of this p by 2 n multiples, p by 2 multiples of this n, 2n, 3n, etc. p minus 1 by 2n, and distribute them into disjoint sets A and P according as the residues less than p by 2 and greater than p by 2. Okay, so consider the A. A equals set A1, A2, etc. to AK, where this AI congruence to Tn mod P. What is T? So 0 less than or equals, 0 less than A less than P by 2 and T less than or equals P minus 1 by 2. We distribute the least positive residues of these multiples of n, p minus 1 by 2 multiples of n, into two disjoint sets A and B, such as A is A1, A2, etc. AK, where AA congruence to Tn mod P and AA lies in between 0 and p by 2 with a T less than or equals p minus 1 by 2. And B, what is B? B equals B1, B2, etc. Bm. So clearly in such a way that Bj congruence to S into N mod P or Bi congruence to Sn mod P, where p by 2 less than Bj less than p, Bj lies in between p by 2 and p, then S less than or equals p minus 1 by 2. Means we distribute this least positive residues according as it is less than p by 2 and greater than p by 2. When this less than p by 2, it includes in A. When it is greater than p by 2, then it includes in B. So A lies in between 0 and p by 2. In second case, Bj lies in between p by 2 and p. Okay, clearly this A intersection B is empty. They are disjoint as well as what is A union B? A union B consists of how many elements? It is m plus k elements. They are distinct. So A union B consists of m plus k elements. But what is this m plus k? M plus k is nothing but P minus 1 by 2. Okay. M plus k equals P minus 1 by 2. Now, define another set C. C equals some set of all C1, C2, etc. Cm, where each Cj equals P minus of Bj. Cj equals P minus Bj. Okay. So what is Ci? Surely this 0 less than Ci less than P by 2. P minus of Bj. P minus of Bj means, yes, it consists of P minus 1 by 2 elements. Cj equals P minus Bj. So these Ci's and A's are lies in same interval, 0 and P by 2. Okay. So the elements of A and the elements of C lies in same interval, which lies in which lies in the interval 0, P by 2. A lies in between 0 and P by 2, as well as Ca lies in between 0 and P by 2. Clear? Now there is a claim. This A intersection C is empty, means A and C are disjoint. How it is possible? If not, suppose A equals some Bj. If not, to prove A intersection C is empty, we just assume A equals Bj. What is A? Sorry, A equals what is A and C, not a Bj. Sorry, A equals some Cj. What is Cj? Cj means P minus Bj. Clear? For some I and j. That means what is P? P equals A plus Bj. Sure. P equals A plus Bj means P equals A plus Bj means A P divides P equals A plus Bj means A plus P divides A plus Bj, that is A plus Bj is congruent to 0 mod P. Clear? But what is actually AA? Tn. So that means AA plus Bj congruent to 0 mod P. But we know that Tn, AA means Tn. So Tn is AA means Tn. So Tn plus, this means AA plus Bj congruent to 0 mod P means Tn plus what is Bj? Sn. So Tn plus Sn congruent to 0 mod P. Agree? So Tn plus Sn congruent to 0 mod P means n into T plus S congruent to 0 mod P. Also, agree? N into T plus S congruent to 0 mod P. But what is our assumption? N is incongruent to 0 mod P. So there is only one possibility. This T plus S congruent to 0 mod P. Agree? What is T plus S? What is T? T less than or equals P minus 1 by 2 and S less than or equals P minus 1 by 2. Therefore, T plus S less than or equals P minus 1. Clear? Since T less than or equals P minus 1 by 2, S less than or equals P minus 1 by 2, therefore T plus S less than or equals P minus 1 means it is strictly less than P. Clear? So clearly T plus S is also n incongruent to 0 mod P, also T plus S is incongruent to 0 mod P. So that is, but we have A plus Bj is congruent to 0 mod P. This is impossible, means A equals Cj is impossible, thus A intersection C is empty. So our claim is justified. Okay. Yes. So there are three distinct sets. A is A1 etc. AK, B B1 etc. BM, C C1 etc. CM. Now we also show that A union B consists of P minus 1 by 2 elements, as well as A and B are disjoint. Then A and C are also mutually disjoint. Enough. Okay. But A union C consists of how many elements? A consists of K elements, C consists of M elements. So A union C also consists of M plus K elements. But what is M plus K? M plus K is P minus 1 by 2. Agree? Okay. Means, now listen. So we know that A union C consists of M plus K elements. M plus K means P minus 1 by 2 elements. What is A union C? A union C equals set A1, A2, etc. AK, comma C1, C2, etc. Cm. Agree? Okay. So A means A union C contains P minus 1 by 2 integers. Okay. All of these are integers. So A union C consists of P minus 1 by 2 integers which lies in closed interval 1 and P minus 1 by 2. Which lies in closed interval 1 and P minus 1 by 2. Okay. That means A union C equals set 1, 2, 3, etc. to P minus 1 by 2. Agreed? Okay. Therefore, the product of numbers in A union C. What is the product of numbers in A union C? That is A1 etc. AK into C1 etc. Cm. That means that is 1 into 2 into 1 into 2 into 3 into etc. to P minus 1 by 2, which is nothing but P minus 1 by 2 factorial. Okay. Yes. That means P minus 1 by 2 factorial equals this one, A1 AK etc. into, A1 etc. AK into C1 etc. C. Now consider that one. Means P1 etc. 1, 2, 3 etc. up to P minus 1 by 2 means P minus 1 by 2 factorial equals A1 etc. AK into C1 etc. Cm. C1 etc. Cm. That is A1 etc. AK into, what is C1? C1 means P minus B1 by Cj is P minus Bj etc. P minus Bm. Okay. Then multiplies, what you get? It is minus 1 power m into A1 etc. AK into B1 etc. Bm. By all the terms P minus B1 etc. If you open this brackets, P minus B1 etc. into P minus Bm, all the terms except the last one, consists of the term P. So all of them are divisible by P. So it is minus 1 power m A1 etc. AK into B1 etc. Bm mod P. Okay, mod P. Clear? Do you get it? Okay. So A1 etc. AK into P minus B1 etc. B minus Bm. Then all the terms except this B1 etc. Bm minus 1 power m into B1 etc. Bm. Except that term, all the other terms consist of an element P. Therefore, it divisible by P. So P minus 1 by 2 factorial is congruent to right side can be rewrite as minus 1 power m into A1 etc. AK B1 etc. Bm mod P. Enough? Means which is congruent to, left side is congruent to minus 1 power m into, what is A1 etc. AK, B1 etc. Bm, n into 2n into 3n into etc. into P minus 1 by 2n. Why? Because A1 etc. AK, B1 etc. Bm, they are the least positive residues of this n, P minus 1 by 2 multiples of n. So it is n, 2n, 3n etc. P minus 1 by 2n mod P. Enough? Okay. That is congruent to minus 1 power n into, it is n, 2n, 3n, so it is how many n are there? So it is n power P minus 1 by 2, there are P minus 1 by 2 terms, so it is n power P minus 1 by 2 into, what's the means? 1 into 2 into 3 into etc. P minus 1 by 2 means P minus 1 by 2 factorial mod P. Okay, that means P minus 1 by 2 factorial is congruent to minus 1 power n power P minus 1 by 2, P minus 1 by 2 factorial mod P, but P minus 1 by 2 factorial is incongruent to 0 mod P. So from there you have 1, so you can cancel this P minus 1 by 2 factorial, then 1 congruent to minus 1 power n into n power P minus 1 by 2 mod P. Agree? Okay. So minus, that means since the congruence relation is symmetric, so it is minus 1 power n into n power P minus 1 by 2 congruent to 1 mod P. Sure? Okay. That means minus 1 power n into n power P minus 1 by 2 congruent to minus 1 power 2n mod P. Agreed? 1 can be rewritten as minus 1 as minus 1 power to n. That means you have as again from there we have n power p minus 1 by 2. N power p minus 1 by 2 is congruence to minus 1 power n mod p, or n power p minus 1 by 2 is congruence to minus there is minus 1 power, minus 1 power m, not n, it is minus 1 power m, so it is minus 1 power m, so it is 2m, so it is finally n power p minus 1 by 2 is congruence to minus 1 power m mod p. Okay, clear? There is minus 1 power m into a1 etc. Yes, okay. So n power p minus 1 by 2 is congruence to minus 1 power m mod p. Clear? Yes. But what is Euler's criterion? By Euler's criterion we know that it is n by p is congruence to n power p minus 1 by 2 mod p. So combines these two results. N power p minus 1 by 2 is congruence to minus 1 power m mod p, but also n by p is congruence to this one. So from here what do you get? N by p is congruence to minus 1 power m mod p. Agree? That means p divides n by p minus of minus 1 power m. But what is p? P is an odd point. This is possible only when the difference should be 0. That means n by p minus 1 power m equals 0, means n by p equals minus 1 power m. This is what is Gauss lemma. Agree? So when n is incongruence to 0 mod p, then the least positive residue of p minus 1 by 2 multiples of n. If m exceeds this p by 2, then n by p is minus 1 power m. So this is our proof. Okay. So first we construct two of the sets A and B. That is depends upon the residues less than p by 2 and greater than p by 2. From there we can again construct another set C. Then we show that this A union B as well as A union C consists of p m plus k, means p minus 1 by 2 elements, as well as A intersection B and A intersection C are empty. So again we use the number of elements in A union C is p minus 1 by 2. So the number of their products, and after that, after some manipulations, we use the Euler's criterion. Then finally we have n by p is minus 1 power m. Agree? Okay, this is Gauss lemma. Now we prove another result. So you consider, let m be the number defined in Gauss lemma. M be the number defined in Gauss lemma means m be the, what is m? Let m be the number of residues. What is m? M be the number of residues which exceeds p by 2. That is stated in Gauss lemma. So now the next result shows that let m be the number defined in Gauss lemma, means m be the number of residues exceeds p by 2. Then m congruence to, then we show that m congruence to sigma t ranges from 1 to p minus 1 by 2. Sigma t ranges from 1 to p minus 1 by 2. Greatest integer tn by p, integer part, or greatest integer part tn by p, plus n minus 1 into p square minus 1 by 8 mod 2. So this is an important result. When m be the number of residues which exceeds p by 2, then m congruence to sigma t ranges from 1 to p minus 1 by 2, integer part tn by p, plus n minus 1 p square minus 1 by 8 mod 2. When n is even, what happens? When n is even, when n is odd. When n is odd, what happens? N minus 1 is even. So it is n minus 1 is even means it's a multiple of 2. Therefore, when n is even, the second case is m congruence to sigma t ranges from 1 to p minus 1 by 2, greatest integer tn by p mod 2. That is the result. How to prove this one? So what is m? m is the least positive residues of the p minus 1 by 2 multiples, n, 2n, 3n, etc. p minus 1 by 2, n which exceeds p by 2. That is what is m defined in Gauss lemma. Agreed? Now take a typical number. Let it be t. So come to the proof. Consider a typical number Tn, t into n. Tn which divisible by p. Tn divided n by p. P divides Tn. Okay. So, on examine the remainders of the size of the remainders. When you Tn divides, the number Tn that which divide p, then we examine the size of the remainders. What is Tn by p actually? We have Tn by p, t into n. Tn by p is its integer part Tn by p plus fraction part Tn by p. Integer part Tn by p plus fraction part Tn by p means 0 less than or equals Tn by p strictly less than 1. Okay? 0 less than or equals Tn by p strictly less than 1. Clear? Sure. So what is t into n? Means Tn equals p into integer part Tn by p plus p into fraction part Tn by p. Clear? Okay. That is, just to take it as p into Tn by p as some Rt. This is just to take it as some Rt where 0 less than Rt less than 1. 0 less than or equals Rt less than 1. Agree? That means t into n equals p into integer Tn by p plus Rt. Clear? Okay. So what is Rt? Means Rt equals t into n minus p into integer part Tn by p. Mark it as 1. Okay. Now, let A and B are any two sets, which consists of the least positive residues of this p minus 1 by 2 multiples of n, according as the least positive residues less than p by 2 and greater than p by 2, same as in Gauss lemma. We can construct the two sets A and B as same in Gauss lemma. So clearly A intersection B is empty, as well as A union B consists of p minus 1 by 2 elements. Agree? So now consider therefore R1, R2, etc. R p minus 1 by 2. These are the remainders. R p minus 1 by 2 equals A union B. Clear? The set R1